In the distant and mysterious valleys of space where stars twinkle against the dark mantle of night lies a vast galaxy that draws the eyes of astronomy lovers, dreamers, and writers. This galaxy is named Andromeda, and today we will make a grand journey to its heart, to the very center of the galaxy. A tantalizing adventure, mesmerizing with bright colors and the promise of new discoveries, begins right here. The Andromeda Galaxy, or M31, is our nearest stellar neighbor. On a clear night, it can be seen in the sky with the naked eye. It is located about 2.5 million light-years away from Earth, and its diameter is about 200,000 light-years. And while this seems incredibly far away, it's actually not. Unlike the others, the galaxy has a bright halo or giant glowing cloud made up of stars, as well as very thin ionized gas. If this halo could be seen without magnifiers in the visible spectrum, it would be 3 times the size of the constellation of the Big Dipper. The area of the huge halo around the Andromeda Galaxy is huge and is about halfway across the disk of the Milky Way. In some places, it even bumps into our galaxy's own halo. Yes, in fact, the galaxies are incredibly close to each other. We begin our journey as we fly through the spherical component of M31. We are getting closer and closer to directly approaching the disk of the galaxy with noticeable spiral arms. However, the Andromeda Galaxy, unlike the Milky Way, has a significantly thickened disk. According to the standard cosmological model, most galaxies were formed by mergers or absorptions of small satellite galaxies, and the presence of a blurred, thickened disk in the Andromeda Galaxy is a sign of just such mergers. Using spectra different in age and type of star, it is possible to calculate the dispersion, that is, to establish how much the speed of a given star differs from the average speed of its nearest neighbors. The results are very interesting. The older the stars are, the older the dispersions and velocities, and higher. That is, it is much more likely that young stars are quietly rotating around the center of Andromeda, while stars in which the nuclear reaction is running out are moving at tremendous speeds. Moreover, even for the calm stars in Andromeda, the dispersion is 3 times that of the Milky Way stars. This clearly indicates that the galaxy M31 has a much more complex and eventful history. Many spiral arm segments are observed in the disk of the galaxy. In the inner regions of the galaxy, they are distinguished mainly by dust, while in the outer regions, they are distinguished by supergiants and regions of ionized hydrogen. M31 contains more than 400 globular clusters. Among them, the Mile 2 cluster is the brightest cluster in the local group, which has a mass between 7 and 15 million solar masses and is possibly the nucleus of a past collapsed dwarf galaxy. On average, globular star clusters in the Andromeda Galaxy are more metallic than those in the Milky Way. It is also interesting that clusters with a large number of stars, in terms of age, are present in Andromeda, occupying 3 ranges, 100 to 500 million years old, about 5 billion years old, and a third between 10 and 12 billion years old. In the Milky Way, by comparison, globular clusters are almost uniformly old, with ages ranging from 10 to 12 billion years, and there are no young clusters at all. The presence of young clusters in Andromeda is probably due to its voracious appetite, that is, to devour irregular galaxies in the past. In addition, there are star clusters in M31 that are intermediate in characteristics between globular star clusters and dwarf spiral galaxies, the analog of which have not been found in the Milky Way. Although their luminosity and colors are the same as those of ordinary globular clusters, they differ only in their very large radii on the order of 30 parsecs. Andromeda's interstellar medium consists of gas with different temperatures and dust, enough of which is present here to be observed in the form of dust lanes that partially obscure the light from the northwestern side of bulge. The dust lanes, and there are more than 700 of them, are clearly visible due to the large inclination angle of the galaxy plane. About 4,000 regions of active star formation from ionized hydrogen are known in Andromeda, as well as 26 supernova remnants and another 20 candidates for such objects. In addition to these, more than 4,000 planetary nebulae are known, and it is estimated that there should be about 8,000 in the galaxy in total. At least 35,000 variable stars of various types have been discovered in M31. First of all, these are Cepheids, bright stars with a certain relationship between period and luminosity by which we can determine their distance. Most Cepheids have periods ranging from 5 to 125 days. Other known types of Cepheids include bright blue variables, Lyrae-type variables, long-period variables, and variables like the RR of the northern corona. In the Andromeda galaxy, about 50 new stars erupt on average per year, and a total of at least 800 such objects have been recorded here. The ratio of the frequency of new starbursts to the luminosity of the galaxy is rather low compared to other galaxies, which may be due to the low rate of star formation. There are also about 2,000 known X-ray sources in M31, X-ray binaries and supernova remnants, as well as evolved white dwarfs with high temperatures. Some sources are observed in globular clusters in the galaxy. The brightness of the M31 cluster is higher in X-rays than in the globular clusters of the Milky Way. Another difference between the sources in the Andromeda galaxy and the sources in our galaxy is that they are concentrated in the center. At present, only one candidate exoplanet, provisionally named PA99N2, has been discovered in M31, but there can be little doubt that there are millions or even billions of planets in the Andromeda galaxy, orbiting its many stars, filled with lifeless atmospheres or perhaps other flora, fauna, organisms, and creatures. Finding planets outside the solar system is extremely difficult because planets do not emit light. All exoplanets that have been confirmed to exist are within our galaxy, but as optical and data processing techniques advance, we will be able to find more planets each year farther out in the universe. In the meantime, we've approached the central part of Andromeda, called the bulge or spheral compaction, and the stars at the center of the galaxy and the brightest part of the galaxy's spherical subsystem. This image, taken by the orbiting telescope, shows the crowded, like a space bus, and very bright central region of the Andromeda galaxy. The bright dot to the right of center is a group of stars around the galaxy's black hole. The blue dots scattered throughout the image, on the other hand, are ultra-blue stars that have prematurely shed their outer layers of matter, exposing extremely hot cores. It is likely that there are many other similarly hot stars in this central part of Andromeda that are in earlier stages of their lives, but they are too dim for us to detect right now. In our journey through the Andromeda galaxy, we have come close to the very heart of the Andromeda galaxy. This image is the clearest image of the galaxy's core ever taken in visible light. A supermassive black hole with a mass of over 100 million solar masses is at the center. The event horizon, the closest region around the black hole where light can still penetrate, is too small to see, but it is near the center of the compact cluster of blue stars at the center of the image. The compact cluster of blue stars is surrounded by the larger double core of M31. The double core is an elliptical ring of old, reddish stars orbiting the black hole but more distant than the blue